Welcome everyone. Today we're going to continue talking about partial fraction decompositions. And to get started, we're going to review over kind of our two main techniques for actually how we find the coefficients A, B, C, and so on. We might have more. And in the examples we saw last time, the strategy we were using was to plug in various x values. So we had this equation, and what we would do is we would look for our distinct linear terms. And those distinct linear terms, we would choose the corresponding x value. So for instance, if we had the linear term something like x plus 2 in our equation, well, we would pick then x equals negative 2 to actually plug into the equation. And the reason is we're going to get a bunch of cancellation. So we saw that in a few of examples last time. Now, we don't necessarily need to pick the corresponding x value. We could just pick nice and easy x values, and it would still work. So x equals 1 is always good. X equals 0 is always a nice one. And maybe even something like negative 1. So you could do the same strategy using just these nice and easy x values. Work is going to be very similar. The strategy we're going to look at in the next example is actually comparing coefficients. So we're going to have our equation, which involves powers of x and then also our a, b, and c terms. And the idea with this strategy is we're going to kind of match up our powers of x and then just compare the coefficients in front of each of our x powers. So this is another helpful strategy as well. And you can use really a combination of these two strategies. So whichever one you like better, that's the one to use. So let's see this comparing coefficients strategy in action. And that's what we're going to see in our next example, example 4. So we're going to find the partial fraction decomposition of the function 2x squared minus x plus 4 over x cubed plus 4x. So we start by noticing that our denominator here is not factored. So we need to factor that in order to see what our terms are. We're not going to do anything to the numerator, so that's just going to stay at 2x squared minus x plus 4. And let's factor our denominator. So how is that going to factor? Well, we have an x cubed here, and then we also have a 4x. So both of those have an x in them. So we can factor out an x. And then we're left with an x plus 4. And if we notice, this x plus 4, or this x squared plus 4, is not going to factor any further. We'll actually see why in a few minutes. But for now, we'll just say this is an irreducible quadratic. We'll actually check this in a few minutes. All right, so that x squared plus 4 is an irreducible quadratic. The x, that's just a linear term right there. So we have one linear factor and we have one irreducible quadratic factor. So once we have our denominator factored as much as we can, we're going to write our decomposition, the general form. So it'll be a over our linear term, so a over x. And then we have our irreducible quadratic term. So that'll go in its own fraction, x squared plus 4 in the denominator. And the numerator, the format for those irreducible quadratics, is bx plus c. And for our constant terms, we just keep going down in alphabetical order here. So let's start with a, b, c. Probably the easiest way. If you want to use subscripts, you could do that. All right, so this is our general form for our partial fraction decomposition. Now, we're going to take this, and we're going to take this equation right here, and we're going to multiply both sides by our denominator. So let's rewrite that. So we have 2x squared minus x plus 4 over x times x squared plus 4 is equal to a over x plus bx plus c over x squared plus 4. And we're going to multiply both sides of this equation by our denominator. And it's usually helpful to use the factored version of your denominator because you can see where all the cancellation is going to happen. Same thing on the left, or on the right rather. And then you just go through and do the canceling. So this is kind of the fun part. On the left, everything's going to cancel except for that numerator term. So we're going to be left with just a 2x squared minus x plus 4. And then what's going to happen on the right? Well, we're going to distribute this whole thing that we're multiplying in. We're going to distribute it to the first fraction. And when we do that, the x in front is going to cancel with the x in the denominator. So we're going to be left with a times x squared plus 4. And then we distribute. So we take this same thing that we're multiplying in, and we're going to multiply it into our second fraction. Now when we do that, the x squared plus 4s are going to cancel. So we'll be left with bx plus c times x. So this is our equation. And our strategy that we saw last time was we could take different x values and plug them into this. And we could do that here. So, we could look for our linear term, plug in x equals 0, figure out a, b, and c. We could just plug in some nice and easy x values, so maybe like x equals 1, x equals -1, and we could solve for a, b, and c that way. Perfectly fine to do that. Just to see something different, let's try the comparing coefficients method. And how we're going to do that is we're going to just multiply everything out here on the right. Won't do anything on the left just yet, but let's multiply everything out on the right. So we get a times x squared plus 4a, and then we get plus bx squared plus cx, and we distribute all that. And what we're going to do is we're going to we want to compare the coefficients of our x terms on the left with the coefficients of our x terms on the right. So let's kind of get this in a nice order and combine like terms on the right. So if we look, we have an x squared term here, and we have an x squared term here, so we can just add the coefficients. So we get a plus b times x squared. Then we have a plus cx. Just go down the order now. And then there's no x term here, so 4a. And we know this is, we're not going to do anything with the left-hand side. All right, so now we have this equation where we have a polynomial on the left, a polynomial on the right, and we're just going to go through and compare coefficients. So let's start with the 2 on the left. Let's start with our x squared. And we're going to compare the x squareds. And we're looking at just the coefficients, the terms in front of the x squared. So we're going to set 2 equal to a plus b. So the only way two polynomials can be equal to each other is if the coefficients are equal to each other. So the 2 in front of this x squared must be equal to whatever a plus b is that's in front of this x squared. Then we go down, keep going. So in front of our x, our single x term, what do we have on the left here? We have a -1. And what do we have in front of our single x term on the right? Well, we have a plus c. So that tells us -1 is equal to c. And so finally, we look at just the lone constant terms that, really coefficients of like x to the 0. We have a 4 over here, and we have a 4a over here. So that means if we set those equal to each other, 4 must be equal to 4a. And now it comes down to just solving those three equations, and it's not too bad. We already know what c is. This one we can solve for a. So we get a is equal to 1. And then we can take that result for a and plug it back in up here. And when we do that, we get 2 is equal to 1 plus b. So b is equal to 1. And there we go. We've compared the coefficients of x squared, x, and x to the 0. And we got three equations that we were able to solve for a, b, and c. And so finally, we just need to plug everything back in to actually get what the exact decomposition is. So let's write it all out. And yeah, why not? I'm going to rewrite our function here. What is a? The only thing that, just pay attention to, you've done all this hard work, all this factoring, all this algebra and whatnot. Just make sure when you're plugging in the right coefficients. So just kind of keep the order correct. So our a value is 1. So we're going to get a 1 over x. Plugging in a equals 1 there. Then for b, what is my b value? It's 1. So I'm going to have 1 times x over an x squared plus 4. And then what is my c value? Well, that's negative 1. And so we end up with our partial fraction decomposition there. And so this is just to illustrate what it's like using the comparing coefficients strategy. So sometimes this is a little bit easier. Sometimes looking at just plugging in x values is easier. Sometimes you can just use a combination of the two of them, and that helps as well. Alrighty. So we need to look at a little bit more details here about why this method works. So first, factoring is the main reason why this works. And there's a main result, and it has a very descriptive name. It's the fundamental theorem of algebra. And it basically asserts that every polynomial with real number coefficients can be factored into either linear terms or irreducible quadratic terms. So this is really the behind the scenes of why partial fractions is working, is because every single polynomial that we're going to see, every polynomial with real number coefficients, can either be written or can be factored down. Can be factored into linear terms, maybe repeated linear terms, irreducible quadratics, or maybe repeated irreducible quadratics. So even if you're given this polynomial and you have no idea how to factor it, technically you can factor it. So the fundamental theorem doesn't actually tell you how to factor it, just tells you that you can. So factoring is generally going to be the tricky part of, our work here. And so we do come across these irreducible quadratics, just like we saw in the last example. So things like x squared plus 4 or 3x squared plus x plus 2, they cannot actually be factored any further into linear terms. So we can't break these apart anymore. And, the reason for this is just the real numbers, they're not enough. So in order to factor these further, we actually need to work with complex numbers. Now, we're in a real variable calculus course, so we're not dealing with complex numbers. So this is as far as we're going to get. So it's okay if we have an irreducible quadratic. We can still work with that. But it's going to be helpful to identify, how do we know if a quadratic can be factored any further, or how do we know if it's irreducible? And there's kind of a few things to think about. You can just try setting the the expression equal to 0 in solving for x. If you can get a solution, then yeah, it can be factored. If it's equal to 0, it can be factored. So with this x squared plus 4, we want to think, can this ever equal 0? Or does this, if we were to set this equal to 0, does it have a solution? And that's kind of the thought process. Can x squared plus 4 ever equal 0? If it does, then we can actually factor it down further. So let's think about that. Can x squared plus 4 ever equal 0? Well, x squared is always greater than or equal to 0. Plus 4 is always greater than 0. So when we take x squared and plus 4 and we add them together, we get something x squared plus 4 that's always going to be greater than 0, no matter what x is. So there's no way this is equal to 0 because, well, we know it's always greater than 0. So the fact that x squared plus 4 never equals 0 tells us that it cannot be factored. And that really means it's irreducible. Can't be factored any further. We're stuck with it as is quadratic. Another way to check, so you can sometimes just think your way through these things. So x squared plus 4, why is it irreducible? Well, x squared is always greater than or equal to 0. Plus 4 is always greater than 0. So there's no way when we add those two things together that they're equal to 0. Another way to check this is with our quadratic formula. So, 3x squared plus x plus 2, how do we show that this is irreducible? Well, we could just try our quadratic formula. So let's remember what that says. It says x, if we were going to try. So let's try solving, take our questionable quadratic here and set it equal to 0, and then try solving that for x. So 3x squared plus x plus 2 equal to 0. Let's try solving that. So how would we do it? Well, normally we would try to factor, but maybe we're trying to factor this and we're just getting stuck. So what's our go-to strategy in that case? Well, quadratic formula. So what does it say? X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So b is the number in front of the x term. So we would get a negative 1 plus or minus the square root of 1 squared minus 4. A is the number in front of the x squared, so 3. And then c is the number by itself, so 2. And then all over 2a. And if we simplify this, what do we get? We get negative 1 plus or minus the square root of 1 minus, what is that, 24 over 6. And then if we simplify a little bit further, we get negative 1 plus or minus the square root of negative 23 over 6. And negatives under square roots, that's not a real number. So the negative under the square root there that's what really tells us this is irreducible. So we're trying to solve this equation. We use our quadratic formula. We're going along. Everything feels okay. And then we get down to this negative under the square root. And that means there is no solution. So this equation does not have a solution, which means it cannot be factored anymore, which tells us it's irreducible. So that's another way to kind of check whether a quadratic is irreducible or not. All right. So there's one other technical point that we really haven't mentioned so far, and it's that partial fraction decompositions do not immediately work for all rational functions. So there is one other thing we're going to have to check. And so first, what is the definition of a rational function? We've been kind of working with this. It's a polynomial p divided by a polynomial q, where these are just polynomials with real number coefficients. So that's a rational function. Now there is one extra definition that we want to make here, and that's the degree of the polynomial. And that's just the largest power in our polynomial, largest power of x. So when we're looking at our rational function, we can talk about the degree of the polynomial in the top and the degree of the polynomial in the bottom, in the denominator there. And we have to pay attention to that because, as we're going to see, we can only do a partial fraction decomposition when the degree of the numerator is less than the degree of the denominator. So it's going to be helpful to think of rational functions as polynomial divided by a polynomial, and then to also remember the definition for degree of polynomial. It's just the largest power of x. And normally we write this as we just kind of do a little abbreviation, the degree of polynomial p. And so just the warning here, we've kind of mentioned it, partial fraction decompositions only work for rational functions where the degree of the numerator, the polynomial in the numerator, is less than the degree in the denominator. So we need to have higher powers of x in the denominator for rational partial fractions to work. Now, all's not lost. We can still make partial fractions work. So in the case where the degree of our numerator is greater than or maybe equal to the degree in the denominator, we have to use polynomial long division first. And so that's what we're going to try with this rational function. So we have a polynomial divided by a polynomial, so it's a rational function. But if we notice, the degree in the numerator here is 4. So the degree of our polynomial in the numerator here is 4, and then the degree in the denominator is 3. So we need to, when we work with a rational function, in order to get the partial fraction decomposition, we have to have a smaller power in the numerator, a smaller degree in the numerator. And so we're going to actually, when the power is larger, it means that there's actually we can actually do some of the division here. So that's what we're going to do with polynomial long division. So we start writing this kind of how you would, if you remember all the way back when you used long division for numbers. And I might just, that's a square root sign. I did it again. Well, that's the long division sign. All right, so we're going to take this polynomial that was in our denominator and we're dividing it into our numerator. And so the way long division works is we look at the first term and we want to make it match up with the first term here. So what would we need to multiply x cubed by to get x to the 4th? We would have to multiply by x. So we get x to the 4th. And then we have to multiply everything else by x. So we're going to get negative x cubed minus x squared plus x. And then we're going to subtract. Then we're going to subtract this. And looking at it, hold on, if you're writing, we need a little bit of extra space here. So generally when you write this out, you want to leave a little bit of space for any missing powers of x. So in our numerator here, we're going from x to the fourth down to x squared. Let's rewrite that. And I'm going to write the 2x minus 2x squared plus 4x plus 1. I'm going to kind of write those over here. Leave a little bit of space here. All right, so just to help you remember it, not really necessary, but it just helps. So what we're going to do is we're going to subtract this line from this line up here. And so the x to the fourths are going to cancel. We're going to be subtracting, there's really a 0 here. There's a 0x cubed. So when we subtract the negative x cubed, we're going to get positive x cubed. And then we have a negative 2x squared, and we're subtracting a negative x squared. So that's going to give us a negative x squared. Then we have a 4x, and we're subtracting an x. So that's going to give us plus 3x. And then finally, we have a plus 1, and there's no constant term that we're subtracting off, so we're going to be left with plus 1. All right, so far this is our remainder. This is what's left, what's going to be left after our division. But we want to look, is the highest power here less than the highest power here? The answer is no. So we can keep going. There's still a little bit of division we can do here. So we just compare. How would we make the x cubed here, or how would we make our x cubed here match up with what we have over here? And they already match. So we don't have to multiply by anything. So we're just going to put a plus 1. And let's take that plus 1, multiply it into this. So we're going to get x cubed minus x squared minus x plus 1. Again, leaving any spaces if you need to. And now let's subtract. So we're going to subtract this line from the line above it. So the x cubes are going to cancel. And then we have a negative x squared and the double negative on this x squared. Those are going to cancel. Then we have 3x plus x, so we're going to get a 4x, and then we're going to get a 1 minus 1, so that'll be just 0. So if we go through all this, and we get down to a point where the power of x that's left is smaller than what we're trying to divide in, that means we're done with the division. So for this one, we have x plus 1 that we've been able to divide out. So let's kind of write out the result here. So here's our original rational function that still had some division we could do. And we were able to completely divide out of there an x plus 1. So that's nice. And we were able to do this work until we got down to this 4x. And at this point, the power of x was smaller than the power of x in our denominator. So that's going to be our remainder term. So that's going to become part of our remainder term. So we're going to have plus 4x over, and we're still dividing that by our denominator. It's just we can't do any more division. That's as far as we can go. So we were able to completely divide out an x plus 1, and then we have this leftover 4x divided by x cubed minus x squared minus x plus 1. So that's generally how polynomial long division works. And then once we get to this point, then we could actually do partial fractions on that fraction. So let's try it out. Example 5. Let's actually take this rational function and do the partial fractions with it. So what we saw was with polynomial long division, that was necessary because the power of x in the numerator was larger than the power of x in the denominator. So we had to do some polynomial long division. And this is what our result was. So that's a necessary step. Now we want to factor this denominator. And this is maybe the tricky part. So how do we factor that denominator? It's a cube. Nothing immediately jumps out at me that we're going to have something that factors here. So one way, if you're kind of stuck on how to factor, is to look for an easy solution. So try a few kind of nice integer values here. Maybe like x equals 1 or x equals 0 or x equals -1. Those might be easy enough. And the way you can check that they're a solution is just to take one of those x values, plug it into the thing you want to factor, and see if it gives you a 0 or not. So we're trying to factor our denominator. And let's try the x equals 1. Let's plug x equals 1 into this. When we do that, we get, what do we get? We get 1 cubed. Well, we get 1 minus 1 minus 1 plus 1, which is equal to 0. So that actually tells us this thing does factor. And x minus 1 is a factor. So we can use that to our advantage here. So we want to factor our denominator. Nothing immediately clear jumps out. So we look for some easy solutions. You know, try x equals 1, try 0, try -1. Plug x equals 1 into the function you're trying to factor. And if you get 0, well, that means that it's a factor. So this part here, that everything is equal to 0 when we plug in that number, that tells us we do have a factor. And so since we plugged in x equals 1, the corresponding factor then is x minus 1. All right, so that tells us this thing does factor. We can factor out an x minus 1. And so the question is, how do we figure out the remaining piece? Well, polynomial, we do the long division again. That can be helpful. So to find this missing portion here, we can use long division. So if we know a factor, if we know one of our factors, we can use long division to find, what the remaining pieces are. So let's actually do that. Let's take x minus 1, and we want to divide that into our denominator there. And we want to see what we have left over. So we're going to go through long division again. So what would we have to multiply x by in order to get it to match up with the x cubed? Well, we would have to multiply by an x squared. So when we multiply that, we would get an x cubed. And then when we multiply the -1, we get -x squared. Do our subtraction. So the x cubed minus x cubed is going to give us 0. The -x squared minus a -x squared will give us 0. And then we're just going to have minus x plus 1 left over. Now the power of x here is 1. The power of x here is 1. So that means we could still keep going. And so what would we need to do in order to get this x to match up with that negative x? Well, we'd have to multiply by negative 1. So when we do that, we get negative x plus 1. And then we subtract. And then everything just cancels out perfectly. So that tells us this x squared minus 1 that's the remaining term. And now x squared minus 1 can be factored. And this one's probably a little bit easier to factor now. So we know that that factors into what? X minus 1 times x plus 1. And then we see two actual factors, two repeated terms here of this x minus 1. So we can just group those together. All right, so we've factored our denominator. Now let's actually, we're at a point. So this one is tricky because first we had to use polynomial long division to kind of factor our, or to kind of do any remaining division that could be done, get it into a form that we can do partial fractions. The denominator wasn't a nice one to factor. We had to do a little bit of work. So we looked for an easy solution. That it was kind of a desperate attempt, and it worked out okay. So we got an easy solution. We had to use long division to find out, what the remaining piece is, and we were finally able to get this thing factored. So now let's go and do the partial fractions. So we want to write out our decomposition. And for now, let's just work with this fraction. So we're just going to be working with this fraction here. And if we do our decomposition, now how do we handle these repeated linear terms? Well, we just give a fraction for each linear term. So x minus 1 is a linear term. It gets its own fraction, a over x minus 1. And then we're going to do another fraction for x minus 1 because there's two of them. And then we increase the power. So in this, we'll have a x minus 1 squared. If it was x minus 1 cubed, we would have a third fraction here. It would be plus c over x minus 1 cubed. But we don't, so we only have those two fractions. And then finally, we have this x plus 1, and that's just a linear term that's repeated once, so it gets its own fraction, c over x plus 1. All right, so we've written out the format for our decomposition. Now we're going to actually go through and multiply both sides of this by our denominator. And it's helpful to use the factored version, so let's multiply on the right here. And so everything on the left is going to cancel very nicely. We're just going to have a 4x that's left. And what's going to happen on the right side? Well, we're going to take this whole thing and we're going to distribute it to that first fraction. So when we do that, one of the x minus 1's here is going to cancel with the x minus 1 here. So we're going to have an a times x minus 1 times x plus 1. Then when we take this and distribute it to our second fraction, the x minus 1 squareds are going to completely cancel, and we'll be left with a b times x plus 1. And then finally, we distribute to our third fraction here, and the x plus 1's are going to cancel. So we have c times x minus 1 squared. And now we can we have a few things we could do. We could compare the coefficients of our x squareds and our x's and our our x to the zeros. But let's plug in for x. So we have a lot of linear terms here. So what are our linear terms? Well, x minus 1. So let's plug in x equals 1. When we do that, on the left side we get 4. And then on the right side, wherever I see that linear term of x minus 1, that's just going to become 0. So this is why this technique helps so much, is because it's just going to cancel off this whole piece. And it's going to cancel off this whole piece. And then for this middle term, if I plug x equals 1 in, I'm going to end up with b times 2. Not too bad. We'll be able to do that. You know what? Let's solve that. Not too bad. We can divide both sides by 2, and that gives us b is equal to 2. So we've already found one. What's our other linear term? Well, our other linear term is x plus 1. So let's plug in the corresponding x value for that, which would be x equals negative 1. And so as we're looking through, on the left, let's plug in, we get negative 4. But then on the right side, wherever I have an x plus 1, that's just going to get canceled out. The whole thing's going to become 0. So this whole first piece with a is going to cancel out. This whole piece with b is going to cancel out. And then we have our c term here, which is going to be c times negative 2 squared, which ends up being negative 4 is equal to c times 4, which is going to give us c is equal to negative 1. And then finally, we still need to figure out a, and this is where we might actually need to just pick an easy x value. So we've kind of exhausted all of our linear terms. So pick an easy x value, maybe 0. 0 is always good. So when we do that on the left, we get 0. And then on the right, we get a, negative 1, plus 1. And then b times 2, or b times 1, rather. And then plus c times negative 1 squared, which is just 1 again. And so we end up, what is this equation? We get 0 is equal to negative a plus b plus c. And we already know what b and c are, so we can just fill those in and figure out what a is. So a is equal to b plus c. So a is equal to 1. And then finally, we just kind of take our a, b, and c values, plug them into our decomposition, and that's what our function is going to simplify to. So we're still going to have that x plus 1 in front, and then we're going to have a, which was 1, so 1 over x minus b, or x minus 1, plus, what was the second one? B over x minus 1 squared. So we know what b is. It's 2. So we're going to have 2 over x minus 1 squared. And then finally, our c value was negative 1. So we're going to end up with c over x plus 1. It's probably helpful to just write that as subtraction. And so there is our nice decomposition. Whew. A little bit of work for that one. But we got it. We got it. So we had to do some long division. We had to get a little creative in how we actually factored our denominator. But actually, once we had it factored, then this part wasn't so bad. All right, so that just about does it. So to summarize partial fractions, the first step is just to make sure you have to use polynomial long division. And you only need to do this if the degree of the numerator is greater than or equal to the degree of the denominator. So you need to get it into the format where there's smaller x terms in the numerator as compared to in the denominator. Once you have that set up, once you've gone through the long division, if you needed to, then you factor the denominator. And then from there, you break your fraction apart into the various forms as needed. So based on the multiplicity of your linear and irreducible quadratics. And then you solve for a, b, and c. And so the hardest part generally for this process is actually factoring out the denominator. Sometimes you might not really know how to factor it. So, just a few tips. You can use the quadratic formula. So if you have a quadratic equation that you're trying to solve, try and use the quadratic equation. If you get x equals 2 as a solution, well, that means x minus 2 is a factor. Or you can do what we did in the last example and just look for some easy solutions like 0, 1, -1, and then use polynomial long division to kind of keep going with it to find the remainder. All right, so next time we're going to see why does partial fractions, why is it so helpful when we are interested in integrating? But we're going to see that next time. So we'll see you then. Bye-bye.